Hello everyone. Now I'm going to present our work, Muses Efficient Multi-User Searchable Encrypted Database. I'm Tung from Virginia Tech. This is a joint work with my advisor, Hoang and Dr. Behnia from University of South Florida, Dr. Guajardo from Bosch. We all know that end-to-end encrypted data outsourcing systems are increasingly popular, and they can provide strong security guarantee against adversary compromising the server. However, encryption also prevents the capabilities that can execute on plaintext data, such as querying analytics. A fundamental feature that the user would like to do is the ability to search over their encrypted data in a secure manner without revealing the content of the data and the query to the server. Therefore, searchable encryption has been proposed to handle this matter. A common issue with searchable encryption is leakage-abuse attacks, which exploit patterns by observing the operation of the user. For example, search pattern is a repetition of search queries. Result pattern is a repetition of matches in search results. And volume pattern is the number of matching documents. All these pattern leakage attacks aim to uncover the user's data and query. There have already many practical searchable encryption platforms. In our work, we propose Muses, which can support multi-writer, high-O statistical information, including search result and volume patterns. Also, Muses achieve minimal user overhead regarding both computation and communication cost. About system and threat model, we consider setting with an honest reader who holds a public and private key pair. Our system can have an arbitrary number of writers, in which any writer can be adversarial. Each writer has an independent database, and L servers in which up to L-1 servers can be corrupt. We assume the adversary is semi-honest. In our system, the writers contribute and share data with the reader, and the reader is the one who executes search over a database of writers. To support keyword search efficiently, we build a search index beside document collection. Our search index is a table where the rows correspond to documents and the columns correspond to keywords. The value 1 indicates the appearance of the keyword in the document, so each row is a bitmap for the keywords of the corresponding document. To update a document, we change the corresponding row of that document in the search index. To search or to find out which documents contain a specific keyword, we obtain the column corresponding to that keyword. With that design, the search index will be very large when the number of keywords is significant. We use Bloom filter, which provides efficient membership testing to compress the search index. For each keyword, we hash it to different locations in the Bloom filter and set their values to 1. We do this for every keyword, then we obtain the search index with Bloom filters instead of bitmaps. Now, to retrieve documents matching a keyword, we need to obtain multiple columns that the keyword is hashed to instead of a single one as before. Using Bloom filter may incur false positive, but we can configure parameters to achieve a low rate. To protect the confidentiality of the search index, we need to encrypt it before uploading to the server. We use key homomorphic pseudorandom function proposed by Behnia et al. In 2013. I'm going to call it PRF for short. With this technique, we can split a key into two random paths where the PRF output with the original key is equal to the sum of PRF output with the split keys and a small error. We encrypt each value of the search index by adding it with the output of the PRF. Next, I'm going to describe our search protocol. A primitive we use is distributed void function, or DPF for short. This technique uses multiple servers to hide the element being queried, and it requires computation overhead linear in database size. For example, the user creates and sends DPF queries corresponding to the requested index, and the servers will evaluate and return responses so that the user can assemble and obtain the query element. So we can apply this technique to search without revealing search patterns. The reader uses DPF to retrieve secret shares of the query column, add them together, decrypt, and obtain the final output. However, this incurs a significant amount of communication overhead, which is linear in the number of documents, since the column dimension of the search index is the number of documents. So our approach to avoid this overhead is to design oblivious protocols to offload most overhead to the servers and only return a small number of matching results to the reader. After the previous step, DPF evaluation, the servers hold secret shares of the search result, but still in encrypted form, since, as I mentioned before, the search index is encrypted. To remove encryption and convert them to secret shares in plain text form, the reader sends the splits of PIF keys to the servers for decryption. Because the keys are split randomly, no server can learn the actual key to uncover private data, and also these keys are random. It doesn't reveal such patterns. After this step, each server holds a secret share of the search result in plain text form. The servers can broadcast their results to each other to open the search output, but doing so reveals result and volume patterns. To hide these patterns, we designed two new multi-party protocols operating on secret share values. One is called oblivious padding, and another is oblivious shuffling. Our multi-party oblivious padding and shuffling are built based on secret share shuffle chase et al. In 2020. First, we developed multi-party oblivious counting protocol to count the number of matches in the secret share form. The input is arithmetic secret share data vector in the previous step, and the output is a secret share of the counting result. The reader can obtain this counting number and then compute the number of necessary padding values. Our oblivious counting is efficient, which requires only one communication round and lightweight computations in the online phase. Most overheads is done in pre-processing phase. In fact, our oblivious counting is more efficient than generic MPC like Gapple circuit when the counting values are small. In the next step, by counting the number of matches, the reader creates and sends secret shares of padding vector values to the servers, which are appended to their output in the delegating decryption step. We assume the search result size is bound by a number, so the size of the padding vector is also bound under the same value. With n documents, then the total padded size will be the sum of the number of documents and the search result size. Our purpose is to always return the same number of matches for all queries to high volume patterns. At this step, the server has yet opened the result, since that will reveal result patterns and padded positions. To hide result patterns and padded values, we develop multi-party oblivious shuffling protocol. The input is arithmetic secret shares of a data vector, and the output is a permutation for each of the first L-1 party, and the open shuffle data vector for the last party. As illustrated here, for the first two servers, each holds a permutation, whereas for server 3 holds a shuffle data vector in plain text. In the final step, the reader receives permutations and permuted data vector from the servers. The reader then applies reverse permutations to recover the original data, also remove padded values, and obtain the final search output. Regarding search complexity, the reader communication overhead is bound by the search result size. The reader commutation overhead is linear in the number of documents, and the server commutation is linear in the number of documents times Bloom filter size. In fact, server computation is fast because it only includes additions and multiplications over small integer numbers in the range of 16 bits or 2 bytes. Apart from keyword search, our Muses supports permission revocation efficiently, which happens when a writer needs to revoke the reader's search permission. The way we choose to implement it for long-term privacy is to re-encrypt the search index of the writer with new sealed key, which is so-called key rotation. This is a good practice recommended by companies and even mandated by regulations. Our high-level idea is to secret share the new sealed key for multiple servers so that the servers can cooperate to update the encrypted search index securely without revealing the new sealed key and the data of the writer. To evaluate our Muses, we use Amazon EC2 instances with octa-core high-performance CPU. Our client is a laptop quad-core i7. Our implementation is in CPP. We compare our Muses with state-of-the-art searchable encrypted systems. Regarding the reader's bandwidth, Muses is up to 2 orders of magnitude smaller than Nori, which also hides patterns and about 6 times larger than HSE, which offers multi-writer feature but leaks all patterns. About the end-to-end latency, Muses is 2 to 4 times faster than Dory and 100 to 600 times faster than HSE. For permission revocation, the writer's bandwidth is up to 2 orders of magnitude smaller than Dory and HSE, which do not have this built-in capability. And the writer's latency is up to 4 orders of magnitude faster, and the end-to-end latency is 2 to 6 times faster than Dory and HSE. Our implementation can support up to 6 servers. Adding more servers can enhance the security level as we allow up to L-1 out of L servers can be grabbed. We evaluate with more servers and also under different network latencies between the servers. In the case of 60 millisecond latency, keyword search takes 3 to 5 seconds longer than with 1 millisecond latency, while permission revocation takes 1 to 4 seconds longer. In conclusion, our Muses is a multi-writer searchable encryption scheme that can hide all statistical information, including search result and volume patterns, while featuring minimal user overhead for search and permission revocation. We publish our source code here. Please visit it for more information. This is the end of my presentation. Thank you for your attention.